last lecture we learned the correlation-based demodulator. Right? This is an optimum receiver, and we have two different ways of design of optimum receiver. First way of design is correlation-based demodulator, and this is a block diagram for correlation-based demodulator. So what we are talking about is this red box. Right? We get a received signal, and this received signal is a transmitted signal plus noise NT. And based on the received signal, what we do is that we already know what is transmitted. So if you use an antipodal signal, then we know that it's going to be either positive value or negative value. Right? So we already know the perfect signal that we are receiving, we are expect to receive. So we probably expect either this one or this one, right? That's a perfect answer. So since we already know this, when you receive some noisy signals, what we are trying to do is that we are trying to calculate the correlation between received signal and the node answer. Right? Try to find the correlation. And in these antipodal signals, like positive or negative, eventually when you calculate the correlation here, so basic operation of this correlation is same as convolution. So therefore, right here, when you calculate this correlation in continuous domain, it's something like this, right? That's what you're going to get. So you always get like increasing like this and going down like this. So you're going to have a peak at TB. So that's why we are going to sample it here at TB, because we are going to get the maximum value or minimum value at TB. So once you do that, eventually at the output here, you're going to get this value or some negative value. Okay? So just looking at here, if that is a positive value, then we just decide later that, oh, this one must be transmitted. And if this is negative, then we just make a decision like this. Right? That's antipodal signal. Similar way, in orthogonal signals, we basically run the two different correlators. And we just calculate the two different correlators and measure the same way, y1 and y2, and we are gonna pick the one of these with a bigger value, larger value. Okay. Yesterday, one of you asked me a question like, since if we use orthogonal signals, right? Then P1, it's like this. On P2, psi1, psi2 is gonna be off. So when you use this kind of very special case of orthogonal signals, that's what we learned, right? On, off. That's orthogonal signals. If we use this way, then let's say it's just a noise signal like this. Now we're going to calculate the correlation between these two here. So you're going to get some correlation value here. You're doing correlation here also, right? You're trying to calculate the correlation between this and this. But the problem in this case is that this is 0. So you multiply this one with this, it's going to be 0 anyway. So correlation anyway is 0, right? So that means it's 0. So something is wrong, right? Something is wrong. Yeah, that's the question. In fact, that is true, but what we are looking at here is a very general picture of orthogonal signals. These signals, on-off. Okay? This is orthogonal signals, but this is one example of orthogonal signals. Okay? This is not a general orthogonal signals. There are many orthogonal signals. Let me give you another example. Okay, this is S1 and S2, right? Same here, S1 and S2. I can make this. This is orthogonal signals. S1 and S2, I can make it this way. It's still orthogonal. Okay? Make another way. I can make this one as S1. This is also S2, orthogonal signals. There are many millions of different ways of making the orthogonal signals. This is also orthogonal, a lot of orthogonal signals. Okay? This is like a very special case where this one is 0, so that's why maybe you think that, when you have a correlation, when you calculate correlation, it's all 0. For this special case, that is true. But the block diagram we are looking at here is a general case. Let's say we are using this orthogonal signals. In that case, you're going to use this here. So of course it's not 0, right? You're going to get something here. Okay, do you get the message? So the picture here, this binary orthogonal signals, this correlator block is a general, general picture, general block diagram for any orthogonal signals. You have many different way of designing orthogonal signals. I'm just giving you a simplest way, but don't think that you're going to get 0. Okay, you're going to get 0 only for this one, which is very special case. So for every orthogonal signals, this block will apply. So this is a general block diagram for all the orthogonal signals. Okay, so let's move on here. The previous picture was a block diagram, and this slide shows you equations. Equation is actually pretty simple. What we are doing here is to calculate the correlation. This is a correlation. But look at here, this is yt. So when you draw the yt, let's draw this is t. You can draw the yt. Yt is going to look like this, something like this. Okay? Yt, this yt here is here. That's yt. So this is a block diagram. You have two inputs, and based on that you do integration. Mathematically, this is the equation. So these two are same thing, basically. You get yt like this, and next thing to do is you're going to do sample. You're going to get the sample at t equal to t sub b. So when you put the sampling here, after sampling, you're going to get this, okay? Because t equal to tb. So that means continuous time correlation output like this. But when you sample it at this point, you're going to get this value. That value is y t sub b. That's the output here. Eventually, that's the output. So that output is this one. This one. This one, right? That is the output. But what we can see here is that this output right here, ytb, that is the output value. That is this output value here. But this output value here is not constant. That is random. Okay, this value actually is random. Why is it random? Because noise is added, and noise is added. And here, noise is random. Noise also go into the integration and go all the way. So eventually, ytb is some constant sm. Sm means s1 or s2. Okay, m equal to 1 or 2. So, for example, s1 plus n, and s1 is constant, but n is random. So therefore, this ytb is random. Every random variable has its own statistics, right? Random variable, so that's a random, and we can put this as a variable, then we call that as a random variable. Right? Every random variable has its own statistics, such as PDF, CDF, something like that, right? And this particular random variable here is Gaussian. distributed. So its PDF is Gaussian, like this. And the difference between the noise is that our noise is NT in time domain, right? And when you put that as this is a time domain view, like this, time domain. But when you look at that from the statistics point of view, the amplitude will show Gaussian. That's a statistics, right? So you get a 0, because when you take an average, most likely the average is 0. Sometimes you get a high value, sometimes low value, like minus 0.7, sometimes plus 1.2, right? So when you put that in statistics here, 1.2 is somewhere here, maybe minus 0.7 is somewhere here, and sometimes you have a very large negative value. So put that all together and draw the histogram, if you like, then you're going to get this picture. So we're talking about same thing here, all of them same. This is time domain view, this is statistics, PDF. So this is the PDF of noise. What about the PDF of this random variable? It's the same. Why? Because what we are getting here is actually just constant plus noise. And this noise has this statistics, so you just add the constant, then what that means is this one is just shifted by S1. So now we're going to have the same Gaussian, but the middle, the mean is going to be S1. Because this one is shifted. The 0, the middle point, the mean moves to S1. So we have S1 here. So that is a random variable for this one. That's the case when you transmit S1. If we transmitted S2, same way. This one may be S2 in that case. So in that case, S2 may be somewhere here, and 0 is in here. So you're going to get another Gaussian like this. So that's why in binary transmission, you're always going to see this kind of picture here. This kind of picture. 2 Gaussian, and one Gaussian has the mean S1, the other Gaussian has mean S2. Right? So we always going to see that kind of picture. Okay. So let's come back here. So it is very important to remember this picture. Okay? Very important. We're going to look at the details in a minute. Okay, so let's move on to the second optimum receiver. So far we learned the correlation-based modulator. The idea, okay, this is, again, the idea of correlation-based demodulator is try to find which one is more close, which one moves more same, right? Which one has a higher correlation. We only have 2 choices, right? Because this is a binary. Let's say if that's the antipodal, we know that maybe this is transmitted or this is transmitted. We have only 2 choices. And now you receive something. You receive something. So what you're trying to do is, which one looks closer? Okay, which one looks similar? That's the idea of correlation-based modulator. So we calculate the correlation between these two and correlation between these two. So if it looks similar, that means high correlation. It's simple as that. That's what we learned so far. And second design of optimum receiver is matched filter. Okay, so let's look at the matched filter now. Matched filter is designed pretty similar. This is a matched filter design for antipodal. This is for orthogonal signals. The difference between the previous correlation-based modulator and this matched filter is that the previous one was previous one, the correlation-based modulator looks this way. Now the matched filter looks this way. It's pretty similar, right? We have two same input, but this one, we don't have any integration. This one has the integration, but this one does not have integration. But instead, this one says filter. We have a filter here. We have filter. Okay, filter. That's it. We have only just one filter. That's it. After the filter, we do the same thing. You're going to do sampling at the same time, and you're going to get the same output. Actually, you're going to get the same output. So this one and this one, both are optimal, which means that you should get the same output. If one is better output, then this is not optimal. Okay? Both are optimal, meaning both ones should give you the same answer, and both are same optimal. So let's take a look at this filter design, optimized filter. So before that, let's just let me remind you one basic thing. Since we have a filter here, let's take a look at very basic signals and system. Let's say we have some filter here. This is filter. You have input to the filter. You have output to the filter. So let's say the filter input is xt, output is yt. And every time when you look at the filter, we always think about the filter response. Or we call that as impulse response of the filter. You heard about impulse response, right? Impulse response. Impulse response. So let's call this impulse response as ht. So basically, what is impulse response? As it says, impulse response is like when you put the impulse, the input is impulse. Then you're going to get some output. Okay? Since you get input as an impulse, you're going to get some output. That output is impulse response. Why? We put impulse, and that is a response from the impulse. So that's impulse response. So when you get an impulse in, you're going to get ht out. Okay? So we can measure it. We can measure it. That's impulse response. So now, based on these, we know that what is the impulse response of the filter. Once we know the ht, we can call that as an impulse response. Now later, we're going to use another input, xt as input, and using the same impulse response, and we measure the yt. And yt is what? xt convoluted with ht. So it's a convolution between xt and yt. That is a basic relationship. Right? Coming back here, this is also filter. But this is a special filter called the matched filter. But anyway, this is filter. So we have the same relationship. Here, we call this yt. That is the output of the filter. Input to the filter is rt. So let's put that to the relationship. Yt, which is the output, equals to rt, input, convolution, with its impulse response. And what is the impulse response in this case? In this case, we have a second input here, right? That is this one gives the idea of what is the impulse response. So your filter is designed based on this. So simply speaking, you have some signal in. In this case, inside the filter, you're going to flip left and right and use that as the impulse response. So simply speaking, we have P, right? P. And I'm going to flip left and right. So that is like this. So I'm going to use it that way. So what is this one? This is same as impulse response of the filter. That is impulse response. So it's actually the same thing. Only difference is that in that case, there is a matched filter, so it's a little bit special filter. Why is it special? Because it is a little bit special. You have this input to the filter, and I'm going to left and right. I'm going to switch to left and right and use that as impulse response. So your impulse response of the filter is this. So it looks a little bit special. So that's why we call that as band filter. You're going to use the same thing for these things, for thermal signals. And I'm going to look at that in the next slide with the equation here. Okay, when you look at this equation, it's much easier to understand. So as I said earlier, for our matched filter, we're going to use this one as impulse response. Okay, when you look at this, right? When you look at this, look at here. This one is psi TB minus T. So basically, when you have minus T, okay, when you have P, okay, let me give you an example. Let's say my psi T, let's say, looks like this. Just the example. If my psi T looks like this, then what does this look like? Minus T. Minus T means flip left and right. So this one probably look like this. But let's say you have a 0 here. Here's a TB. Then where is the 0? 0 is going to be here. Because think about here, right? This is just a simple minus. So flip it this way. Flip it this way. So that's going to be minus TB. Like this, right? Like this. We have original psi T is here, 0 TB. And since I put the minus here, just flip it like a mirror. Like a mirror, right? Flip it like this. This is going to be psi minus T. So you're going to have minus TB to 0. That's minus T. That's not what we want. What we want is this one. So that's why you're going to add a TB. So add a TB here. Add a TB. In that case, what are you going to get? 0 TB. So that is my impulse response. That's why you're going to do it this way. Psi TB minus T. So this equation here is not complex. It's simple actually. What you're going to do is you have original psi T, just flip it left and right, and make it as a 0 T this way. So this is what we need. When you put that equation, this is the equation. Looks simple, right? When you put the picture, that's simple. This is what we want, and this is impulse response of my filter. Okay, that is impulse response. HT. Okay, my HT impulse response looks like this. Now what we want to do is that, as I said, use this one or this one as my impulse response, and I'm going to go through the filter or convolution. So when you put the convolution, this is a basic convolution output. When you have RT as the input, and we have a filter has the impulse response HT, and YT is the output, then YT goes to RT and HT convolution of these two, which is this. This is general convolution. RT and HT convolution, you're going to get YT. This is just convolution. But our HT is this one. So let's replace this into here, because our HT looks like this, right? So put that aside here, then you're going to get this. Let's put that here. So HT minus tau. So let's put that here, T minus tau. Then this is going to be integral. T R tau H minus something like this, right? Not H. Something like this, right? So I'm going to replace this H here into this. Let's put that in here, right? This is what you're going to get. That's the equation. And what is this? This one basically means let's come back here. This is basically means as a correlation, not correlation. This is basically convolution between these two. Convolution of these two. But let's think about this way. Probably easy to understand these things is that so this is my impulse response. Okay? And what is the psi t for our case? Psi t is going to be this. Or this. Because we assume the antipodal signal. Okay, we're going to use antipodal signal. So we're going to use this one or this one. But we can just pick one. So we can use this one as psi. Okay, same as in the previous correlator-based demodulator. In the previous correlation-based demodulator, we also use this one as a psi t, right? We also use that. Same thing. So we're going to use this one as a psi t. So let's take a look at the impulse response. 0 dB. What is the impulse response of this filter? If we use this one as a psi t, ht looks like same. Same. Why is it same? In my previous example, right, I make it triangle. So that's why you can notice that you put the minus, flip it, and slide it, and this is the output. That is impulse response. And you look like this one and this one different. But this one actually is symmetric. So flip it, slide, still same. So in this case, impulse response actually is very same. Very same. Like a very special case. Okay, that is what we are going to use for HT. And what is my input to the filter? This is RT, right? My input is RT. My input is RT. So let's say by RT, my input looks like this. Okay. So that is my input. This is my impulse response of the filter. So now what we're going to do is we're going to do convolution between these two. Then what are you going to get? At yt, you're going to get something like this. And this one looks like exactly same as the previous correlation output. Why? Why is that? Convolution actually is integration. This is just a different way of putting. Okay, this one is I just draw that as a correlation or integration, but this one I just represent it as a filter. But actually both are same, exactly same, right? Exactly same. Think about this way. Okay, simple way is this way. Remember that we discussed the correlation, right? And what was the difference between correlation and convolution? I asked you this question, right? What's the difference between correlation and convolution? Both of them, you need two inputs. Two inputs, right? You have two inputs coming in, and you have one output. In convolution, let's call this x1t, x2t. In convolution, what you're going to do is that in x1t, you make it same. x2t, you flip it, slide. Okay? and you're going to get the output. That's convolution. What is a correlation? In correlation, x1 same, x2 you flip and convolution. You first flip it and then put it into the convolution. Okay? You first flip it and put it into the convolution. Now inside the convolution, flip it one more time. Okay? So simply speaking, in correlation, it's basically like x1 and x2 do not flip, just slide. So difference between correlation and convolution is that in convolution, x2 is flip and slide. Correlation, just slide. That's difference. That's only difference, right? In here, correlation-based demodulator, we are calculating correlation. So, as I said, x1 is here, first input, second input, just a slide. That's what we are doing in the correlation. Now let's look at the matched filter. Matched filter is using convolution. Okay? It uses convolution because internally when you go through the filter, we are doing convolution. But convolution is actually flipping inside. Okay? Inside the convolution, we are flipping. But what we are doing here is that matched filter impulse response, we are flipping here. So what that means is we flip it. First we flip it and then put it into convolution. So before doing convolution, we flip first. Okay? That's what that means. Let's look at the equation here. This is a convolution, but in H, we flip first. That is the second input. Like we are doing convolution, RT is the first input. Okay, you need the two signals to do convolution, right? This is the first signal, maybe this is the second thing. So you are doing convolution between RT and HT, but not HT. Before the convolution, you flip it first. So HT is flipped, and then put it into the convolution. Then inside the convolution, you flip it again, right? So eventually, this matched filter is the same as RT and HT, just slide. Does it make sense? So correlation-based structure, matched filter structure is the same that way. The correlation-based is just slide between X1 and X2. In matched filter, you flip it first and then put it into a convolution. Inside the convolution, you flip it again. So eventually, it's the same as X1T and X2T slide. Okay. Basically the same thing. And all the equations you see is also exactly the same. So eventually, after the convolution, you're going to get the YT. YT looks like this. We're going to do sampling at the T of the TB. So after that, you're going to get this value. That's the value after sampling. This value. That's the sampling. You're going to get this output. That output actually is SM plus N, which is the same output that you get from the correlator design. So we are basically talking about the same design. So it says identical output, same output from both of them. Then the question here is, why do we call this one as a matched filter? The reason we call this one as a matched filter is because your filter is matched to the input. That's why we call that as a matched filter. Generally, right? Generally, when you use a filter, your filter impulse response is nothing to do with the input. Your filter looks like this. Any filter, right? In general, filter has its own impulse response, some HT, and you are going to get some other input. So XT and HT is nothing to do with them, right? Those are very different. This one has its own impulse response. Input is something else. But in this case, in this special matched filter, the impulse response is matched to the input. That's why we call this one as a matched filter. Then what does it mean by matched? Okay, here's what that means. This is a matched filter. Let's say if you get this input, this is the input, right? In that case, what's going to be your impulse response for the filter? Your impulse response is matched to the input. So if the input looks like this, then your impulse response of the filter is going to be this. Flip. That's why we call this one as a matched filter. It is a filter, but impulse response is matched to the input in the sense that it's flipped and looks the same. That's why we call it as a matched filter. And why do we flip? As I said earlier, once we have to flip it first, and then convolution. Then inside the convolution is flip it again. Okay? When you do convolution between these two, you flip it again. Right? Once you flip it again, this one is this, right? And we flip this again, then we're going to get this. And now we slide. Once you slide, right, then at one point you're going to have a perfect match. Perfect match. When you get a perfect match, these two looks exactly the same. Why? Because our filter response is matched to the input. So these two are matched. Looks exactly the same when you get a perfect time matching. And that's the maximum value you can get. Because both looks exactly the same, both are time synchronized, so you get the perfect maximum, like this. You get a perfect maximum. So that's why this filter is very special, that your filter response is matched to the input. Okay. So this is an example. If you get this kind of signal as the input, your filter impulse response is going to be this. When you look at this, right, this is matched to this. How do you know that? Just flip it left and right and slide. Then you're going to get this. So that is, like if the input is ST, your impulse response is S TB minus T. That is your impulse response of the matched filter. So just remember the matched filter concept and what that means as a matched filter. Maybe some of you want to ask a question. A lot of time the input is random. You are not going to get this every time, right? You can get some other things. Then how do you match it? Maybe that's a question, right? What we are matching here is that when we design the filter, your filter is going to match to this. We know what we transmitted, right? Maybe you transmitted this or this in antipodal signal. Let's make some special scenario, okay? Just to help you understand. Let's think about some system. We have some TX, transmitter. We have receiver. Okay. Now let's put an antenna here. And we add a noise in channel. Now let's think about a certain system that we are transmitting this or this. Just make some strange signals. So you're going to transmit only this one and this one. In that kind of system, you transmit one of these. Here. Actually, no. Yeah, let me put it again. So you're going to transmit 0 or 1, but eventually inside you are doing modulation. So you're transmitting this or you're transmitting this or this. So somehow it's antipodal signals, right? But I'm trying to make a triangle, just to help you understand. Okay? In practical system, this is not going to happen, but just for understanding. So you are transmitting one of these two. Of course, there's a noise. So what you're going to receive is some weird signal like this, something like that. Let's say RT. What you receive is some signal like this. Just the example, right? Now inside the receiver, we have a matched filter, and our matched filter. We have a matched filter. We are going to get this one as an input, and we need to use the cosine t. We have a impulse response of this matched filter, and we're going to get the output. So what is the impulse response in this case? We're going to flip the version of this, because this is the answer. We are not going to flip this one, right? This is the input signal, that's true, but this is the this is RT, which is, we call this one as ST, and noise NT. RT is ST plus NT. We are not going to flip this. We are going to flip this one, because this is what we are expecting to receive. This is what we expect to receive. Right? So we're going to flip this one and use that as the impulse response for the matched filter. So your matched filter is going to be matched to this one, ST. Because if there is no noise, ST is going to be the input. If there's no noise, right? So we are going to match it that way. ST is already known. ST is already known, right? You're going to transmit maybe this one or this one. We already know that. So we can design filter based on that, because we know it already. So that's a matched filter. But in our case, or in the practical system, you are not going to transmit these things. So what's happening in the antipodal signal system is that you are transmitting this or this, right? So you are receiving some kind of this, and your HT again looks like this. So you are calculating basically correlation, or you're going to use this one as an impulse response, and through convolution, you're going to get the same answer. And that's what we're going to get here as the output. That output is like this, and you're going to get sampling at the TB. You get the same output. Okay. You probably hear about matched filter several different places in communications. So just remember what it means, matched filter. Simply, matched filter has the impulse response, and that impulse response is matched to the input. Match means flip. That's the story. Let's move on. This slide shows you the frequency domain interpretation. What we just looked at is all time domain, right? You just do slide with time and convolution. All these things is time domain interpretation. What we see here is a frequency domain interpretation. But it's actually the same thing. In time domain, as we said here, S is the input, ST is the input. So impulse response of your matched filter is the flipped version. So this is our impulse response of the matched filter, as I said earlier. That's time domain. So when you flip it and slide like this, okay, and take a Fourier transform and look at the frequency domain, this is the frequency domain. This is frequency domain. Which means that when you have ST, that's the input, take a Fourier transform, then you're going to get SF. So this is a time domain input. This is a frequency domain response of the input. Okay, we are talking about same input, but this is time domain response. This is frequency domain response. But now this impulse response is a flipped version, flip and shift. So once you flip minus t, flip and shift by adding tb, what happened to this frequency response? This is what happened in the frequency response. You know, when you look at the Fourier transform property, okay, remember the Fourier transform property. Let's say ST, you get SF, right? What happens when you do minus t? Then what do you get? It's the frequency. You're going to get this. Okay. What about you add TB? TB is a time domain shift. In time domain shift, when you take a Fourier transform, you're going to get phase rotation. Time domain shift is going to be the phase rotation in frequency domain. So that's why you're going to get this. So that is a phase rotation because of this TB shift in time. You have a minus t, so therefore you're going to get complex conjugate. So that is the frequency domain response of your impulse response. So in time domain, somehow this impulse response is flipped. But in frequency domain, what does it look like? Let's say our SF in frequency domain looks like this. What does HF look like in frequency domain? Maybe we could put 0 here. What does it look like? This one right here, right? This one? This is a phase rotation. Generally, when you look at this kind of picture, there is a magnitude. You know, there's a magnitude response and there's a phase response, right? This is a magnitude response. So this part, what is magnitude of this part? 1. So when you put the magnitude, this part is 1. So we have the same magnitude. Only difference is that the phase is rotating. Like this. Okay? You have phase rotation. So magnitude is not affected anyway. Yeah, so that's our frequency domain. Anyway, so let's move on here. As I said earlier, HT, which is impulse response, and your input ST is doing convolution in time. When you have a two time domain signal and do a convolution in time, that's going to be same as multiplication in frequency domain. We know that, right? Simply speaking, you have ST. We have ST is the input, and filter has the HT as an impulse response. You're going to get YT. We know that YT is same as HT convoluted with ST in time domain. This is time domain. But this one actually is same as we have SF as the input. This is a frequency response of the input. We have HF, which is the frequency response of your impulse response, your filter, and you're going to get YF. So this picture, same. But this is time domain, this is frequency domain representation. The same thing. In that case, YF is SF and HF, right? We know that, right? It's basically the same thing, just looking at from the frequency domain, looking from the time domain, the same thing. So based on that, we know that this is a convolution in time. So therefore, when you take a Fourier transform, we know that it's a multiplication like this, SF times HF. But what is HF? We know that HF is this. That's what we know already, right? So put this HF here, because we already know HF. Put that here. We're going to get this as your output, YF. Look at your YF, looks like this. What is this part? This part. SF times S complex conjugate F. What is this? This part. This part is the energy of your output, energy of your input. Why is that? This one actually is the same as SF square. Okay? That is same as a square. Because we have SF times SF complex conjugate. So this is square. Okay? And what is SF? SF is our frequency response. When you have a frequency response, and when you do square, that's going to be in energy. Energy in frequency domain. So we have a frequency domain, and your SF looks like that. And you do square, maybe you get a similar thing. And what you have inside here is the energy of your output, input, SF. That's your energy. But this, in this case, the energy in frequency domain. There is a theorem called the Parseval's theorem. Did you learn this somewhere? Parseval's theorem basically tells you that energy is conserved. You have some energy in time domain, you're going to get the same energy in frequency domain. That's physics, right? In physics, you should have same energy everywhere. When you have this energy in time, of course you have to have the same energy in frequency. So this is the energy in frequency. This is the time, energy in time. Then how do you get this? You're going to get this because you do a convolution in time. Let's put the convolution. Your H is actually this. You put this H is S flipped version. So flipped version, put that inside, but inside the convolution you flip it again. So eventually you're going to come back to S tau. Because you flip it first and then put it in convolution. Inside the convolution, flip it again. So you're going to get the same thing. That's what I mentioned earlier. Right? So you're going to get the original input and flip two times. You're going to get the same thing again. So it's going to be square. Once you square in integration in time, that's going to be the energy in time. So you're going to get this equation. That means energy in time. That means frequency, energy in frequency. And these two needs to be same. That's what Parseval's theorem. So these are all equations, but that's the whole story. Let's move on to the next one. I think this picture, this slide here, this slide here probably is one of the most important slides in this course, in this whole course. First thing to remember is that we already looked at these two Gaussian. Okay? We already looked at it. So we have a two Gaussian. We have a two Gaussian distribution. Right? We already looked at this two Gaussian here, right? Another thing that you want to look at here is that this is conditional PDF. This is a PDF, probability density function. Why? Because we are talking about random variable here. Okay? Again, why is it random variable? Because noise is random. Noise plus your S1. Let's say you transmit S1. Then in the channel, noise is added. But noise is random. S1 is not random, but noise is random. So you're going to get S1 plus N or S2 plus N. So that's random. So that's why we're going to get these two Gaussian PDF. But looking at here, this is conditional PDF. Why is it conditional PDF? What is the conditional PDF? What's the difference between this one and this? Right here, y is S1. In this case, y is S1 plus n. In this case, y is S2 plus n. Something like this. Actually, that's not true, but that's something like this. Easy to understand. This is probably easier. So what we are doing here is that this is a conditional PDF, which means that this is the probability of y given that S1 is transmitted. So you first transmitted S1. That's given. Right? You first transmit S1 at the transmitter. And what is the probability that I receive? What's the probability of the sample that I receive? That's this one. So y is the received sample. And what is the distribution of the received sample if S1 is transmitted? That's this one. If S1 is transmitted, then even for the received symbol, maybe you get the same S1. That's this probability. But some other times when you have a noise, maybe you receive like S1 plus 0.7, or maybe S1 minus 0.3, something like this, right? So that is a distribution of that. Same way, this here is the probability of received sample if S2 is transmitted. Okay, if S2 is transmitted. So if S2 is transmitted, the mean is going to be S2. And based on that, you put the noise on top of it. And noise is Gaussian. If S1 is transmitted, the mean is S1 and noise statistics on top of it. So we have two. But remember, this is a conditional distribution. Okay, conditional distribution. So we write the conditional distribution this way. If S1 is transmitted, this is statistics of the received sample. If S2 is transmitted, this is noise statistics. This is a statistics of the received sample. Okay. Remember that this is the most important part. That's what we talked about yesterday, right? That part. Let me clean up here. So we have a blue part, blue shaded part, and we have a red shaded part right here, right? The blue area here, blue area, is if S2 is transmitted, but because of a lot of noise, we receive here positive value. So for the receiver, we receive positive value. So we decided that as S1. So that's an error. So we actually transmitted S2, but we received as S1. So that's certainly a big error. Okay, that's blue case. Red case is the opposite way. We actually transmitted S1, but we received it as S2. We detect it as S2. Because there's a lot of negative noise added. Okay? So for example, if this is plus 1, this is minus 1. So transmitter actually transmitted plus 1. Actually transmitted S is transmitted symbol. Let's say that is S1. That is a plus 1. But it's very unfortunate that noise was like minus 1.2. So eventually when you receive it, it was like minus 0.2. So we receive it here. Okay? Then based on the optimum receiver, we learned we're going to decide positive or negative. So this is negative. So our detection in that case is going to be this. So in that case, it's error. And this red part here is the probability of such things. Probability of such event, error event. And that's why we call that as probability of bit error. Average probability of bit error. So what we need to do is we need to calculate what is the average probability of these cases. All the other case, everything is good. We have to worry about this part because this is the error case. So we need to calculate the error. How much is the probability we have error? So that is our concern. That's the most important thing. And this is how to calculate. This calculation is actually very simple. It looks like a lot of equation, right? But let me tell you, it's very simple. But before that, we have to define one thing. There is a function called the Q function. Did you hear about Q function anywhere? We have that in the next slide. There is a function called the Q function. Q function. Okay, maybe we can continue next time.